net positive suction head. Okay, so one learning objective today, basically we're going to define, and this is abbreviated as NPSH, net positive suction head. Define NPSH and use to design a pump system that avoids cavitation at the impeller. Because the impeller is spinning so fast, that's where our cavitation is most likely to occur. Just rotate. All right, so let's just start by looking at a pump system. So we've got a water level, we've got a pump or a tube that, or a pipe that goes inside the water, and it's got some length, it's got some elevation above the water. It goes into a pump, and so we'll draw the pump. It's gonna look amazing, I promise. We've got our impeller spinning inside. There's our eye. Okay, so the water's coming up, and we got a little strainer here. Usually you got some sort of mesh to keep the debris and whatnot from coming in. Okay. So here's our pipe, here's our pump. The water's coming up through the pump into the impeller, and then it's going across the impeller, speeding up. It's getting that angular momentum imparted on it, and then we've got that high pressure over here. So negative pressure over here and positive pressure over here, gauge pressure. Okay, so now let's look at, let me get, where my other pen go? Let's look at what our energy grade line looks like. Okay, so we start here at the water surface elevation, and then as we move towards the eye, we kind of lose some head just due to friction, right? So this is head loss due to friction. And then we meet the eye, we go into the eye. And because the water is speeding up so quickly, the pressure drops really rapidly. So as we go across this impeller face, the pressure just basically drops, plummets really far down to some floor. We'll just call this some arbitrary floor. Now, once we get off of that impeller and we're back kind of into the pipe, that's where that pump head is imparted and the pressure suddenly increases again. And now we're at a normal flow rate. So here the flow rate's like super fast, you know, 30 meters a second or something like that, right? Because that impeller is spinning so rapidly. But now we get back to our normal discharge, our normal flow rate, and that's when the pressure just skyrockets, right? So that's the head that the pump gives to the flow once we get off that impeller face. And then now we're in our pipe system, right? And we start to lose our energy just due to friction once we're in that pipe system. So we've got the head loss due to friction right here. And that's just the system, the length of the pipe, right? And then we have the head loss across the pump face. And this is what our net positive suction head actually is. So in the book, it's defined as H prime S. And that's the drop. And this is equal to the drop in pressure across pump. And so we then are interested in identifying this elevation above the water surface relative to the eye of the impeller, the Z of the pump. So what is that elevation that we can put the pump at such that we avoid cavitation? So this is ultimately what we're interested in. And then we'll just note that this is the head that the pump imparts. So that's the pump head at that given discharge. So let me just write some numbers here. So if this is our first point, right, we just have the energy associated with the elevation of the water. There's no velocity, no gauge pressure. Then we get to the eye of the impeller, so we'll call that point 2. And this is where we have the, this is the available pressure in the system. And so we really want to make sure that the available pressure at point 2 at the inlet of the eye is great enough so that when we cross this threshold and cross the impeller face, we don't go below the vapor pressure. And then our minimum pressure occurs right somewhere on the edge of the impeller. So that's 0.3, and that's our minimum pressure. And so we'll just note that cavitation occurs if P P at 0.3 is less than P vapor. So we want to avoid dipping below vapor pressure between 2 and 3. And so as long as, because 0.3, so the pressure at 3 is where the minimum pressure occurs. So this is our limiting case. So we want to design the system so that the pressure at 3 is greater than the vapor pressure. So that's kind of our limiting case. Okay, so net positive suction head. And let's just think about this. So suction head is when we're talking about negative gauge pressure. When we have suction head, we're just simply saying the head in the system or the pressure in the system is negative, and we have a suction. We want to make sure that that suction stays above vapor pressure. And so NPSH and when you look at pump curves, you usually see NPSHR. This is required. And what this means is we want to make sure that this is the required head at pump inlet to avoid cavitation. And this is usually provided as a curve because it's going to change depending on how the discharge rate. By the pump manufacturer. So let's just look at a pump curve real quick. And you guys will use a pump curve like this for the project. So this is a big old pump that can move a lot of water. And you can see gallons per minute up to 1,800 gallons per minute, liters per second up to 100. So we're moving a lot of water here. And I just drew a fake system curve on this pump system. So that's the red line right here. So this is our pretend system curve. And this pump is going to be drawing water up from a canal to supply a ditch. So for example, the Redlands canal system or ditch system, maybe I'll try to pull a map of that up later. They have a ditch that brings water out of the Gunnison River, goes by my house, not the river, but the canal. And that canal brings water and basically supplies the Redlands with water. And so they have this huge pump house that will draw water out of the canal and then pump it up to these distributary canals in the Redlands, which have a higher elevation than the main canal. So those pumps are sucking water out of the river. Maybe they're like 6 feet above the river or something like that. And we want to make sure that when we have the system curve, and this would be the system curve for the pipes leading up to the pump, or actually no, for the system itself. So this, say we're going to operate the pump at 1750 RPM. So this is our pump curve right here. So this is our operating conditions where the system curve and the pump curve intersect. So we've got the head provided to the system. We've got the discharge rate. And then there's a lot of lines here. So I'll draw your attention to NPSH. And this is at 1750 RPM. So there's different curves for different speeds that the pump's operating at. So where our operating conditions intersect this line, we come across and there's this little y-axis here, secondary y-axis. And so it says NPSH-R, so this is a required net positive suction head. I'm assuming this is in feet, I actually couldn't find it. Pump curves are notoriously bad at units, but or confusing with units because they often have many units. And we'll just read this section and I'll post this as well. And maybe I'll zoom in for you guys. Okay, so it says when the pump is operating, the suction lift, so the suction involved in lifting the water to the pump, is limited by available net positive suction head, which is the corrected atmospheric pressure minus the dynamic suction lift. So we'll define these and actually write the equation here. Minus the dynamic suction lift, vapor pressure loss, and a 2-foot safety factor. So they put in a 2-foot safety factor just to be safe. Meaning, if you didn't have that, the pump could be 2 feet lower, or 2 feet higher. So they're automatically lowering the pump by 2 feet just to be safe because you know it's hard to get these things perfect. Vapor pressure is going to change depending on the temperature of the water, the elevation of the system. And then it says we want to calculate the dynamic suction lift from the low liquid level. So the lowest the water is going to be. And you can imagine in a canal, water is going to come up and down. In a reservoir, water is going to come up and down. So we want to know the limiting circumstances. Okay, so let's go ahead and think about our pump system. We'll just look at this drawing again. And we'll say to kind of start this quick derivation, we so if we go to the pump inlet, so we'll say at pump inlet, we need it such that P2 over gamma, so the pressure at the inlet, is greater than the vapor pressure over gamma plus our net positive suction head or required. or H prime S. Okay, so this is ultimately what we need to calculate to avoid cavitation. So we have the reduction in head across the pump impeller, and we have the vapor pressure. And so we want to make sure that this reduction in head plus the vapor pressure will be greater than our pressure at the inlet. Okay, so let's go ahead and do that. And so we can, I'll just do a quick tiny drawing of our pump here. And so we start 1 here, and then 2 is at the inlet. So P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus our head loss. Okay, so head loss is going to be equal to our head loss due to friction plus any minor losses. And usually we're just thinking about the intake screen minor loss. And because this is a screen, there's actually some decent losses usually at those screens. That's a pretty friction-inducing entrance. Okay, so we know that P1 over gamma is going to be equal to atmospheric pressure in absolute terms, and we are interested in absolute terms for this problem. And then we'll draw our datum here. So this, we'll say this is datum, Z is equal to 0. So we can cross out velocity and Z, but we'll keep P1 because we're concerned about atmospheric pressure. And then we say under our limiting conditions, we want P2 over gamma equal to the vapor pressure over gamma plus the MPSH. And this is our limiting case. So if we do this, because the MPSH that they give us in our pump curve has already 2 feet of safety factor, then we won't have cavitation occur. But if they didn't put that safety factor in, then if we solve this problem, then cavitation would occur when P2 is equal to vapor pressure over gamma plus the MPSH. All right, so let's plug everything in. So we have P1 over gamma is equal to our atmospheric pressure. So P ATM over gamma, sorry, I should do that, is equal to P vapor over gamma. And again, we're substituting this in for P2 plus H prime S. And then Z2, sorry, I didn't put Z2 over here. Z2 is going to be the Z of the pump, right? Okay, so we end up with a lot of terms, but nothing too crazy. And so ultimately we're interested in the Z. So how high can this pump be if we account for our net positive suction head? So let's rearrange and solve for Z. ZP is going to be equal to PATM minus P vapor over gamma minus our H prime S, our net positive suction head, minus V2 squared over 2G, and then minus our head loss. So ZP ultimately equals the maximum allowable height of pump inlet above water level. And this is really the equation that we're interested in typically. But you could imagine a question says, okay, the pump is going to be 10 feet above the water level because that's just the way the reservoir works or the ditch is designed. What's the maximum flow rate that this pump could have to avoid cavitation? So there could be another way to do that problem. All right, so let's go through an example. And I'll just, I got this written out already, so we'll just kind of go through this together. So for example, we have a pump. It delivers 6 cubic feet per second of water at 40 degrees Fahrenheit to an elevated tank. The tank is 65 feet above a supply reservoir. So I think that we'll draw this out, but the pump is pumping water up to the tank. And the pump's going to be above the reservoir to determine the maximum allowable height, but the pump can be placed above the reservoir under these conditions. And so we're saying that the net positive suction head required is 15 feet for this pump under those operating conditions. So we have a pump curve, and we'll have to, we're given the operating conditions, right? So we're given that it's operating at 6 cubic feet per second. And so we need to calculate then, and they gave us the net positive suction head from this curve. And they said that was 15 feet. So now we just need to go and calculate Z. Okay, so here's some more details. We have minor loss coefficient, so the sum of the minor losses is 2.6, and that's the strainer and a bend, maybe something like that. We have 35 feet of 10-inch diameter cast iron pipe, and then here's our E is equal to 0.00085 feet. So this is our equation that we just kind of derived, and we need to make sure that Z, the height of the pump above the water surface, is greater than these quantities. So the difference between atmospheric pressure and vapor pressure divided by gamma, the velocity of the flow in the pipe, the head loss from the entrance of the water through the strainer to the pump, and then that's net positive suction head required. So the drop in pressure across the pump face. Okay, so here's our atmospheric pressure, and I think we're just doing standard conditions here. So that ends up being 2,120 pounds per foot squared. Our vapor pressure, we go to the book, and let me grab that real quick. There we go. So our vapor pressure, standard conditions, so this is what we're working on, 1.19 times 10 to the negative 1 pounds per inch squared. I'll just write assume standard conditions. Okay, so we convert that to pounds per foot squared. Here's our gamma, 62.4 pounds per foot cubes. And they said the net positive suction head required, or H prime S, is 15 feet under those operating conditions. We can calculate our velocity, just Q divided by A. Which ends up being 11 feet per second. So we're calculating all these terms. Now, okay, so we've got our velocity, we've got our net positive suction head that was given, we have atmospheric and vapor pressure, and we need to make sure those are in pounds per foot squared because we're divided by gamma, which is pounds per foot cubed. So that everything comes out to feet, right? We're dealing with feet. So now that we got all those terms, we need to calculate our head loss. And that's going to take a few more steps, right? So our head loss is going to be equal to, using Darcy-Weisbach equation, F times L over D plus the sum of our minor loss coefficients times the velocity squared over 2g. Okay, so we can do Moody diagram, we can do Swami-Jain equation. First, we need to calculate our Reynolds number. So we have our velocity, 11 feet per second, our diameter, 10 inches times 1 foot or 12 inches. And then our kinematic viscosity, which we look up. Density, specific weight. Viscosities of water, table 1.3. Kinematic viscosity, and we said 40. 40 Fahrenheit? 40 Fahrenheit. So 1.634 times 10 to the negative 5 feet squared per second. All right. And then our Reynolds number ends up being 5.4 times 10 to the 5th. Okay, E over D, we got our diameter, 10 inches divided by 12. Our roughness height for cast iron, 0.00085. So here's our E over D. And we can plug that into the Swami-Jain equation, or we can go to our Moody diagram. There's no iteration here, right? Because they gave us the flow rate, they gave us the velocity and the diameter. So we can directly calculate our F value. So the next step is now we just go into our head loss equation. Here's our Darcy-Weisbach. So F times L over D plus 2.6, and that was just given the entrance loss coefficient for the strainer was 2.6. And then that's times the velocity squared over 2g. So we get our head loss of about 6.5 feet over that 35-foot diameter or 35-foot length pipe. So now we can plug everything in. Our height of the pump needs to be greater than the atmospheric pressure, 2,120 pounds per foot squared, minus our vapor pressure, which is 17 pounds per foot squared. And then our gamma, 62.4 pounds per foot squared, or per foot cubed, minus velocity squared over 2g, minus our head loss in the pipe, minus our net positive suction head, which was given. So we end up with a Z pump of 10.3 feet. So that is net positive suction head in a nutshell. I posted a kind of a guide in more layman's terms. The book's kind of theoretical. The guide I put there is just kind of like a little more plain speak about net positive suction head. There are kind of two different terms. Typically, when you see the pump curve, it's going to be the required head, and so that's going to be the head you need coming into the pump to avoid that drop going below cavitation or vapor pressure. So that's R. Sometimes you'll see NPSH-A, and this is the pressure head available at the pump inlet. And that's basically what we calculated for P2. That's going to be the head that is coming into the pump. And sometimes you'll see that terminology. So available is the head coming into the pump. Required is the head. You want to make sure that the available is greater than the required so that you avoid cavitation. And just note that they already put a 2-foot safety factor into that required situation, so that even if it is equal, even if available is equal to required, you should be okay because of that safety factor.